important. Why these topics are important mean these topics you are going to get. Why I told you to attend this class means these topics are very important. You are going to get these topics even in the exam also. So that is the reason we have to cover these topics. So power measurement, microwave power measurement, we will see. So this part already we have covered some portion of this. So microwave power measurement we can do. There are three types of microwave power measurements. One is low power measurement, medium power measurement, and high power measurement. So what is low power? Less than 10 milliwatts is called low power. So starting from 0.01 milliwatt to less than 10 milliwatts, that power is called low power. Medium power is 10 milliwatts to 10 watts. 10 milliwatts to 10 watts power is called medium power. Greater than 10 watts is called high power. So these are the three categories of power. So how to measure these three types of powers? So most of the important questions in microwave or power measurement normally you will get is frequency measurement, attenuation measurement, or power measurement. So these questions you are mostly you are going to get. So power measurement is also very important question. So we'll see low power measurements. So low power measurement can be done either using bolometers or thermocouplers. Bolometer or thermocoupler. So what is a bolometer? A bolometer is used to detect the power. So what is a bolometer? It is used to detect the power. Its operation depends upon, generally bolometers are used. Bolometer is used to measure the power, microwave power, that too low powers. Low powers are measured using bolometers or thermocouplers. So bolometers are used to detect the power. Their operation depends upon thermal principles. What are thermal principles? When a microwave power fall on the bolometer, its microwave power is converted into heat and its temperature changes. In turn, its resistance changes. The change in resistance changes its voltage. So that is the principle of microwave, I mean to say bolometers. Okay, this is the procedure generally used in bolometers. Bolometers are used to measure the microwave power. Its operation depends upon the thermal principle. When the microwave power falls on the surface of the bolometer, its energy, microwave power is converted into heat energy and the temperature changes, its resistance value changes and its voltage also changes. And the resistance, the mic, how much power is absorbed by that bolometer, it's proportional to its resistance. So there are different types of bolometers are there. What are the different types of bolometer? Barometers are there. Thermistors are there. What is the difference between the barometers and thermistors are important. Barometers generally either barometers or we can use or thermistors you can use. Normally instead of thermocouplers, bolometers are used to measure the microwave power. That's why we are mostly concentrating on bolometers. So bolometers, again, there are two types of bolometers. One is barometers and other one is thermistor. What is a barometer? Barometers having positive temperature quotient. So that means you know what is positive temperature quotient. So it's positive resistive quotient. They're having positive barometer. Now, the spelling is Barrettetters. Barrettetters, barometers. These are having positive resistive quotients. What is positive resistive quotient? As the temperature increases, its resistance value increases. That's why it is called barometers. What is thermistors? Is it's having negative resistive quotients. Thermistors having negative resistive quotient. That means what it means, its resistance value decreases as the temperature increases, its resistance value decreases. These two come under the category of bolometers. These two come under the category of bolometers. So generally, how we are going to use these bolometers to measure microwave power is, generally there is a waveguide. So there is a, let us consider there is a waveguide like this. So you have to keep the bolometer. So keep the bolometer like this. So the bolometer, the microwave power is coming like this. The microwave power is incidented on the bolometer. So the bolometer observes the microwave power. Whenever microwave power is observed by the bolometer, what happens? Its temperature changes. Its temperature changes means the power is converted into what? Heat energy. So its resistance changes. Its resistance changes means its voltage changes. Generally, this bolometer never used as independently. It is used in a bridge. That's why bolometer, a balanced bridge bolometer is used generally. What is the circuit is we are going to use? This type of circuit we are going to use. So a bolometer, this is bolometer. So I think in your in your EMI course, you have studied this balanced bridge, all these things. So generally, without application of any microwave power, this is bolometer. Let us consider its resistance without application of any microwave power R1. This is R2, this is R3, this is R4. The bridge is under balanced condition without application of any microwave power. Whenever you are applying any microwave power, what happens? The bridge becomes unbalanced. This is a galvanometer. The bridge becomes unbalanced. To make it balanced, what you have to do? You have to either change the resistance value or the potential. Let us consider in this case, we are changing the potential to make it balanced. So the difference in potential is proportional to microwave power. The difference in potential initially without giving any microwave input, we are applying, the bridge is in the balanced condition, the applied voltage is V1. Whenever we are applying the microwave power, the bridge is in the unbalanced state. To make it in the balanced state, we have to adjust the voltage of the bridge. So what is the adjusted voltage? V2. The difference of these two voltages, the voltage difference is proportional to what? Microwave power. Or else we can use another formula. What is the formula we can use is, using this formula also we can calculate the microwave power incidented on the bolometer. Either of these two formulas are used to calculate the power incidented on the bolometer. So power can be measured either using any one of the technique. One is low power can be measured using bolometer technique. Bolometer, there are two types, either barometers you can use or thermistors you can use. Barometers having positive resistive temperature coefficient, or thermistors having negative resistive temperature coefficients. So we'll move to the second category, high power. How high powers can be measured? So we'll move to the second category, that is most important one, how high powers can be measured. High powers can be measured using calorimetric method. What is calorimetric method? It's a simple method. So the calorimetric method is very simple method. So what is in this method, in a calorimetric method, so there are two types of calorimetric method. In calorimetric, generally calorimetric, again there are two powers, low medium power measurement, high power measurement. Generally high power measurements is there in our syllabus. High power measurements can be done using calorimetric method. So how using calorimetric method, how power can be measured is, so there are flow type or dry type, dry or flow type. There are two types of measurement techniques are there. Generally flow type calorimetric method is used to measure the power in calorimetric method. So what is the procedure used is, in this method, the power is made incidented on the water. Flow type means some water flow or any liquid flow is used to calculate the power. You are doing the power measurement. The flow type, the name itself tells some flow, some microwave observing, or some liquid which has good observing capability of microwave power is taken. Not only water, any liquid which is having good observing microwave power, that type of liquid you have to take to measure the power. That liquid we have to take. In this example we are taking water as a fluid. So let us take, I am taking a fluid, let us consider a fluid I am taking, and here there is a pump is there. For this there is a inlet for this, and there is a microwave load is there. There is a microwave load. To this microwave load, so a microwave power is given to this. So microwave power is given to this. So from this pump, a liquid is coming from this. Here microwave power is coming. Whenever the microwave power is to the microwave power, a liquid is incidented on the microwave power, definitely its temperature will be what? There is a definitely change in the temperature. The heat introduced into the fluid makes temperature difference definitely on the incident power. So what is the temperature difference? What is the outlet temperature? We will see here. This is called outlet temperature. We will measure the outlet temperature, and here the flow meter we are going to use here. So there is a flow meter here. So this is the setup generally we are going to use. So in this method, the power is made to incident on the water flowing at a constant rate through the water load. The heat is introduced into the fluid, um, and the temperature difference is calculated using this formula. P is equal to 4.18 into V into D into Cp into T. T is nothing but T2 minus T1. This is T2, this is T1, temperature difference. T2 minus T1, outlet temperature. T2 is nothing but outlet temperature. T1 is nothing but inlet temperature. These two differences you have to take. What is Cp is nothing but specific heat of this fluid, and D is the specific gravity of the fluid, and V is the rate of flow of the fluid. So if you know all these parameters, use this formula to calculate the power. So this is called calorimetric method. A fluid is flown like this, and a power is flown like this, and there is a temperature difference exists when the fluid is flown in this method. So the temperature difference is taken, and using this formula we are going to calculate the power. So this is what the procedure followed to calculate the power measurement in calorimetric method. And another last one is impedance measurement. Impedance measurement. Last parameter is impedance measurement. How to measure the unknown impedance? Unknown impedance means we have the figure like uh, reflex crystron power supply, reflex crystron, isolator, variable attenuator, frequency meter, slotted waveguide. Here some unknown load you have to, we don't know what is the load. For this load only we have to find out the impedance. First unknown load. Here to the slotted waveguide we have to use detector, and a VSWR meter is connected. By using this one, what you have to do is, whenever you are using unknown load, definitely since the load is unknown, we doesn't know. When the load is perfectly matched, then only you are going to get what? Without any reflections. When there is a perfect matching, then only there is no reflections back. But there is an unknown load you are connecting means definitely There are some reflections towards this one. So there are standing waves are formed. So the standing waves are nothing but like this, the standing waves are formed. So the V minimum is nothing but this one, and V maximum is nothing but this one. Now in this place, instead of unknown load, you replace with the shorted load. In the second case, the setup is same, shorted load you replace. Again, you find out what is the V minimum, what is the standing wave pattern you are getting. Suppose the standing wave pattern, suppose the standing wave pattern, you are getting something like this. If you are getting the standing wave pattern, something like this, if you are getting standing wave pattern, suppose the V minimum, this is the V minimum. Previously V minimum is here, but now the V minimum is shifted towards the left hand side at lambda g by 4 distance. It represents, it is a inductive load. It represents, it is a inductive load. If it is shifted towards the right hand side, it represents the capacitive load. That is one way of identifying whether it is a capacitive load or inductive load. But the thing is, I have to find out the exact load impedance. Are you getting this one? So we have to use this setup. First thing, standing wave pattern we have to see. So standing wave pattern first, without connecting shorted load, unknown load you have to connect. See the standing wave pattern. Now connect the shorted load. So with shorted load, you have shorted load anedi is available in your lab. Connect the shorted load. See where you are getting the V minimum. So previously V minimum and this V minimum you compare. If it is compared to the previous V minimum, your now your V minimum towards the left hand side means it is the inductive, or if it is the right hand side means it is capacitive. So like that you can identify whether it is a capacitive load or inductive load. Or else if you want to calculate the exact value of the impedance, you have to use some formulae. What are the formulas you have to use means I will tell you. What are the formulas you have to use means I'll I'll give you the PDF for these things. Please go through the PDF. So all the formulae, what is the formula? ZL is equal to this formula. I think you got in your EMTL, rho into tan beta delta L, rho minus J tan beta delta L. So ZL is the impedance that you want to find out. What is Z naught? Characteristic impedance. What is Zn? Zn is the input impedance. So rho is the reflection coefficient, and beta delta L is the distance. You are saying some V in, V minimum, V maximum. At what distance you are getting the V minimum? So left hand side you are getting or right hand side getting. That is delta beta delta L. So Z naught is calculated using this formula. So use this formula to calculate. Straight away you have to learn these formulas. So use these formulas to calculate this formula to calculate so the unknown impedance. This is the formula is used to calculate the unknown impedance, but that is the procedure. Whatever the procedure I told, that is the procedure to calculate whether it is a capacitive load or the inductive load. So that is the procedure generally used to calculate the whether it is a capacitive load or the inductive load. So this is about the measurement. So what we have seen in the measurement, we have seen how to measure the frequency, how to measure the VSWR, how to measure the VSWR also very important. Double minima method. Power measurement is very important. Don't leave these 5 topics. Power, VSWR, double minima method, many times it was given. Power measurement is given. And other thing is attenuation measurement, uh, less times it was given. Frequency, power and VSWR measurements are important. For your mid, you prepare at least for frequency measurement and power measurements. Okay, frequency and power measurement. Next, the most important question in this unit is GUNN diode. So in this unit, most of the times it was appeared in university question papers also, that gun diode question was appeared. It's most very important question. What is gun diode? Why it is so important? Gun diode is very important. So what is gun diode? So I'll give the brief introduction about a gun diode. Within 10 to 15 minutes, I'll explain everything. So what is gun diode? It's a two-terminal device. Actually, GUNN diode. You know what is a diode? A PN junction diode. It has anode and cathode. Just like a PN junction diode, GUNN diode is also having a two terminals, anode and cathode. The symbolic representation of the GUNN diode is something like this. The symbolic representation of the GUNN diode is like this. But why we need GUNN diodes? We are already studied about various tubes, microwave tubes in third unit and fourth unit, like reflex crystal power, reflex crystal amplifiers, oscillators, all those things we have studied. But those are high power amplifiers, high power oscillators. But low power oscillators are required. At low powers, generally we are going to use with the small space, low power outputs are required. Means these initially microwave tubes had played very important role in the earlier stages of development of microwave technology. Around 1950s, during World War II, microwave tubes come into picture. So at that time they played a very crucial role at the initial stages. But later, with the invention of semiconductor technology, whatever the semiconductor technology you have studied in VLSI technology, solid state technology come into picture later in 1970s and 80s. From that 1970s and 1980s, for low power applications, these semiconductor technology becomes a leading technology. So for miniaturized size, for low power applications, low cost applications, generally microwave solid state devices are used rather than that microwave tubes. Are you getting why these microwave solid states? These are called, whatever the diodes today we are going to discuss are called microwave solid state devices. Why these are coming to picture means with the invention of microwave semiconductor technology, these solid state microwave technology come into picture. These are used for miniaturized application, that too for low power applications. These come into picture. What are these are having significant applications, advantages. These are having longer lifetime, low operating voltages. They can be used for many applications. They're having wide bandwidth. So what are the microwave solid state devices means? A GUNN diode, impact diode, trapite diode, Barrett diode, tunnel diode. These are the microwave semiconductor solid state devices. Today we are going to see about the GUNN diode. So GUNN diode, GUNN diode was invented by J.B. GUNN. That's why the name came as a GUNN diode. So there was a theory called RWH theory. What is RWH theory? These terminology you please remember, Amma. RWH theory. What is RWH theory tells us? What is R stand for is Redley, Watkins, Hill, Hilsum theory. He explained a mechanism, negative differential resistance, NDR. Negative differential resistance is developed by a solid state semiconductor material. When a voltage is applied to the terminal, that's what he told is indirectly what I mean to say is to a semiconductor material. You know what are the semiconductor materials? Silicon and germanium. Those things already in your EDC course you have studied about it. Now I am going to introduce one more special type of semiconductor device, that is semiconductor material, that is gallium arsenide. What is gallium? It is a third group element. Arsenide, it is a fifth group element. Both are combined together. Third and fifth group elements are combined together. So this is the special semiconductor material is used to manufacture this gun diode. What is the advantage means what RWH theory tells us is to this semiconductor device, a very high voltage is applied to the semiconductor device. Negative resistance characteristics, or else we are calling it as negative differential resistance characteristics, we can observe. What do you mean by negative differential resistance characteristics? Whenever there is a negative resistance characteristics are observed means in this region we can operate that particular device as oscillator. That means gun diode can be used as oscillator. That's what this Redley and Watkin and Hilsum has observed. So what they have taken is they have done the experimentation also. Even Gunn has JB Gunn has done the experimentation. What he has taken is a gun effect. That effect is called gun effect. In 1963, he discovered this effect. That effect is called gun effect. He has taken a semiconductor, a piece of semiconductor bar he has taken. One end is called it as anode, another one is called cathode. A slab of semiconductor bar he has taken, and he applied a very high potential is applied. When after a certain potential, what happens means a bar of not normal semiconductor, gallium arsenide. That means there are various combinations of semiconductor materials as taken. Semiconductor materials satisfying this RWH theory is what are the semiconductor materials that satisfying this RWH theory is gallium arsenide, indium phosphide, cadmium telluride, zinc sulfide. So there are various semiconductor material that satisfy this RWH theory. What is RWH theory? The RWH theory tells us when negative differential resistance characteristics are developed, when high voltage is applied across a solid state semiconductor material, when high voltage is applied. That is called RWH theory. Okay, so J.B. Gunn initially in 1963 he observed that what he observed. So he has taken a slab of semiconductor material, a high voltage, that too a gallium arsenide semiconductor material he has taken. If the voltage is, he applied a potential is applied. When the voltage exceeds a certain limit, what happens is oscillations. That means that not generally we'll call it as oscillations. When a voltage, when an applied voltage exceeds a certain level, so he has seen some oscillations are observed uh, in a particular what in that particular semiconductor slab. That effect is called what? Gun effect. That effect is called gun effect. That's most important thing. So the gun diode, what you have to see is this is the thing you have to explain. Gun effect. What is gun effect? This is also called as transferred electron effect or gun effect. So this can be explained using another theory. So you know in EDC, you have studied in unit 1. So there are different bands are there. There is a valence band is there. There is a conduction band is there. These two are separated by a gap. This gap is called forbidden gap, forbidden energy gap. When an electron want to jump from valence band to conduction band, externally you should apply a voltage which is very high voltage you should apply, which is equal to the forbidden energy gap. What is the forbidden energy gap for gallium arsenide is so 1.43. So you should apply a voltage greater than this 1.83 electron volts. Then the valence electron can move into the conduction electron. Even in the conduction band, what Gunn has observed is in the, so there is a valence band. Even in the conduction band, what he observed is there are some sub-conduction bands are available. So sub-conduction band means, conduction band means again there are some sub-conduction band. So in some conduction band, high mobility electrons are available, but their energy levels are low. Energy level is low. Here low mobility electrons are available, but energy level is very high. This is what he observed. So an electron which is want to jump from high mobility to low mobility, or high mobility to low mobility, so we have to apply an external voltage. అర్థమవుతుందా? So we have to apply an external voltage. So using this theory also we have to explain the concept. So initially what he proposed is, he has taken a gallium arsenide slab, he applied a potential. When it is exceeds a certain voltage, generally it is more than 200 electron volts, what happens? He observed oscillations in that slab. So that effect is called electron transit effect or GUNN effect. So and what are the characteristics? Initially, what happens whenever you are applying the voltage? So the electrons from valence band, they'll move to the conduction band. So the current what increases, the movement of the electrons results current. So the current what increases. After that, what happens? As you go on increasing the voltage, the electrons can move from high mobility to low mobility. But here the mobility is low, so electron movement is very, very less. So the current what? Decreases. What is this region is called? Negative resistance region. What is this region is called? Negative resistance region. Okay, you have to explain this operation using these characteristics, using this valence band and conduction band. So GUNN diode operates in 4 modes. What are the 4 modes of GUNN diode operation? So what are the 4 modes means? GUNN diodes operates. You know what is transit time? We already discussed. Transit time means the time taken by the electron to reach from one electrode to other electrode. One electrode means from anode to cathode is nothing but transit time. So we have taken a slab of this one, anode to cathode. So a high uh, what I mean to say is, so negative resistance characteristics are observed. GUNN has observed negative resistance characteristics are observed when high voltage is applied to a slab of semiconductor device, and or else AC voltage is observed in the slab of semiconductor material. That's what GUNN has observed. Now the wave which is started from anode to cathode, the time taken by this is called transit time. Yes or no? It is nothing but a transit time. The time taken by the electron to reach from anode to cathode is nothing but transit time. So there are 4 modes of operation in GUNN diode. What are the 4 modes of operation is? One is GUNN mode. GUNN mode. Another one is delay